I want to start by clarifying that although I'm presenting this lecture, it's in fact a joint work between Hiranya Sudhasinghe and myself. Hiranya is a PhD candidate in molecular biology at the University of Bern in Switzerland, and he and I have contributed equally to the content that I'll be presenting today. I want to take this opportunity also to mention the fact that we are in the final stages of producing a book on Sri Lankan biogeography, which I'm going to give a quick plug to here. It should be published within the next month or so, assuming there'll be some normalcy in the country by then. All right, with those preliminaries out of the way, let's get started. First off, I'm not going to describe Sri Lanka's northward transit from Antarctica because you've heard about that already. But just to refresh your memory, I should mention that while India and Sri Lanka were rafting up towards Asia, around 66 million years ago, a celestial object of some kind, a comet, a meteor, or an asteroid, collided with Earth on the Yucatan Peninsula of Mexico. And the dust and debris ejected by this massive explosion caused a global extinction. Around 3/4 of all the animal species on Earth were destroyed, including, as I'm sure you'll remember, the dinosaurs. And then, as if that weren't enough, there was an immense spate of volcanism in the vicinity of what is now Maharashtra in India. Around 1 million cubic kilometers, just think of that quantity, of magma were ejected and deposited on the Indian peninsula. And this is the region we now refer to as the Deccan Traps. These events occurred at about the same time, and they decimated the fauna and flora not just of India, but also of Sri Lanka. Very little was left standing on our tiny island as the Paleogene period dawned around 66 million years ago. Evolution was in effect handed a blank slate on which a new chapter of our biogeographic history could be written. And of course, operating over millions of years, evolution is able to work its magic in the most beautiful ways. And so we have the wonderful biodiversity we treasure on the island now, thanks to events largely that are more recent than that extinction event 66 million years ago. But before getting into that, I'm going to quickly give you a summary of Sri Lanka's climate. Climate is the key to understanding everything I'm going to discuss today. As you probably know, the Intertropical Convergence Zone, a region of high rainfall, circles the Earth around the equator, pretty much all around the world. This region receives the highest amount of solar radiation, which results in more evaporation and so more rain. As the sun moves northwards, in other words, as the northern summer progresses, the convergence zone too moves up north across Sri Lanka and up the peninsula of India. This is the southwest monsoon. And then, when the northern winter sets in and the southern hemisphere begins warming up, the convergence zone and its rainfall moves south once more, bringing with it another rainy season, the northeast monsoon. That's a simplistic version, of course, because factors like the Indian Ocean dipole and the El Niño southern oscillation too have big impacts on our weather. But you get the idea. This pattern, combined with the mass of mountains in the middle of our island that characterize our topography, results in Sri Lanka's southwest quadrant receiving a very high rainfall, pretty much year-round. We call this region the wet zone. It receives upwards of 2.5 meters of rain per year, but that isn't what makes the wet zone special. Many places in India, for example, receive 2 or 3 times as much annual rainfall. But take a look at these rainfall charts for 3 dry zone stations in the top row and below that 3 wet zone stations. You can see straight away that what makes the wet zone special is that it has no dry period. I've marked the 100 millimeter per month line on these charts. In other words, they don't have 2 or more consecutive months in which rainfall is less than 100 millimeters. And this is true for many stations in the wet zone. And this is what we call a perhumid climate. So you can see that in terms of climate, the southwestern wet zone is pretty unusual. And not just in South Asia. There's nowhere else between equatorial Africa and Sumatra, a span of more than 7,000 kilometers, that has a perhumid climate like Sri Lanka's wet zone. This means the wet zone harbors rainforests whose plant diversity is unmatched anywhere else, not just on the Indian subcontinent, but also other biodiversity-rich countries like Myanmar and Thailand. You have to go right down the Malay Peninsula to a latitude of about 6 degrees, in other words, latitude of Gaul, before you encounter a perhumid climate again. As you know, Sri Lanka is separated from India by the Palk Strait, which is very nearly spanned by Adam's Bridge between Thale Manar on our side and Rameshwaram on the Indian side. The sea in this area is very shallow, rarely more than a few meters deep, so shallow that only small boats can get across. So if sea level were to go down by, say, 5 meters, a land bridge emerges connecting India and Sri Lanka. Hiranya and I decided to call this land bridge the Palk Isthmus, after the Palk Strait. And that's what I'll refer to it as from this point onwards. So you begin to see that what is now Adam's Bridge, the train of sandy shoals between Thale Manar and Dhanushkodi, was when sea levels were lower, a range of low hills fringing the southern shoreline of a broad isthmus that connected Sri Lanka to India. You can see from this graph down here that if sea level were to go down by just 30 meters, I've indicated that with the red line, it'll give rise to an isthmus that is more than 150 kilometers wide, connecting Sri Lanka to India. Now, that's about the distance from Colombo to Mathura, so you can see that the isthmus was, well, pretty wide. So how often was sea level low enough for this isthmus to emerge from the sea? Well, over the last glacial period, let's say the past 115,000 years or so, sea level was low enough for a wide isthmus to emerge above sea level for more than 80% of the time. Only 20,000 years ago, sea level was 122 meters below present, and the Palk Isthmus was almost 200 kilometers wide. So when our ancestors, the first culturally modern humans, arrived in Sri Lanka probably around 75,000 years ago, they didn't need to come by boat. They walked. And the isthmus was emergent until as recently as about 6,000 years ago. Our ancestors then could hike to Rameshwaram to do their Sunday shopping. Now I hear some of you ask, but what about before that? Well, you can see here in the course of the past 2.5 million years, sea level was frequently less than 30 meters below the present level. And that was enough for a broad isthmus to emerge. And then what happens if you go even further back, say the past 5 million years? Again, the isthmus was exposed for most of that time. Now, although some of the most interesting biogeographical riddles lie in the flora, unfortunately, my botanical friends have been a little slow to use the tools of molecular biology to investigate these questions. So I'm not going to dwell much on the plants here, but you'll see from our book that Sri Lanka's flora contains some of the most fascinating examples of biogeographic disjunctions, species or groups of species that occur in different places, but not in between. And that's what makes the study of our island's biogeography so absolutely fascinating, these disjunctions. So until the botanists catch up, let's move on to the fauna. I kid my botanical friends. In fact, they do some fantastic work. If you haven't seen the red list of the flora published a few weeks ago, you should read the superb geographical analysis presented there on the threatened plants. But I shouldn't digress. As you know, we started off as a part of Antarctica 120 million years ago. But Antarctica wasn't at that time a frozen desert as it is now. It had quite a temperate climate. But do any animals from that period, or their descendants, survive on Sri Lanka now? The answer in the case of the vertebrates is not very much. Perhaps only the geropylid snakes, the blind snakes, these fossorial snakes, which there's a large diversification on Sri Lanka of. But a handful of unusual invertebrates give us a tantalizing view into the island's deep history. There are 5 endemic species of heterometry scorpions in Sri Lanka. The group occurs also in southern India, but their closest relatives are in Africa. And it seems that the African and Sri Lanka-India group diverged at about the time we broke away from Antarctica 120 million years ago. Just a few years ago, colleagues of ours in Kerala discovered a bizarre snakehead fish that lives in freshwater aquifers underground. The occasional specimen swims into a well. In fact, that's how the species was discovered in the first place. The fish has since been assigned to a new family, the Enigmachanidae, and it too may have diverged from other snakeheads when India separated from Antarctica 120 million years ago. Sadly, the fossil record for Sri Lanka's mammals begins only quite recently, within the last 100,000 years or so. My friend Callum Manamendra Arachchi at the Postgraduate Institute of Archaeology of the University of Kelaniya kindly prepared this slide for us. Callum is an expert in identifying animals from which subfossil bone fragments like these come. And as you can see, there were in Sri Lanka 2 species of rhinoceros, 2 species of elephants, a hippo, the lion, the tiger, the wild dog, and the gaur, not so very long ago. Why did these animals suddenly disappear in the past few tens of thousands of years? We think it was probably climate change that caused these extinctions, a loss of suitable habitat. That said, some of these species still survive in India. Unfortunately, the lack of a fossil record means that we can infer our biogeographic history only from the present-day fauna and flora, using molecular clocks and relationships with the fauna and flora of other countries. These help us estimate when the various branching points in the tree of life occurred. But we have to remember that large uncertainties are associated with these clocks. We need to keep this in mind when we make inferences from them. But despite these shortcomings, molecular clocks are very useful when it comes to estimating not just when biogeographic events occurred, but also the sequence in which they occurred. We'll discuss some examples in a minute, but I first want to look at some other Sri Lankan animals that have Gondwanan connections. The closest relatives of the Sri Lankan arthrospherid pill millipedes, for example, these are animals you'll find in leaf litter in Singaraja, for example, live on Madagascar. The 2 groups diverged 90 million years ago when Sri Lanka and India rifted from Madagascar. And then there's the aquatic cascade beetle genus Scoliopsis. You may have seen these diving beetles at the foot of waterfalls. Their sister group too is associated with a Madagascan genus. And then there's the petalid spiders and their cavid snails. They have persisted on Sri Lanka for tens of millions of years, but are altogether absent from India. Their relatives are all on former Gondwanan fragments, like Madagascar and the Seychelles. But remember that Sri Lanka hasn't been connected terrestrially with the Seychelles for at least the past 65 million years. As I mentioned already, the geropylid blind snakes, the ones we used to call typhlops, seem to be the only Gondwanan vertebrates that survived on Sri Lanka after the great extinction that brought the Cretaceous period to an end 66 million years ago. So you can see we know of only a handful, literally a handful, of Sri Lankan animal lineages that trace their ancestry to the time when India first made contact with Asia around 55 million years ago. The Gondwanan signature in our fauna, or for that matter our flora, is very faint indeed, but it is there. So as a conservationist, you must forgive me if I believe that it's perhaps just as important to conserve these ancient groups of scorpions, centipedes, and spiders and snails as it is to conserve elephants and leopards. So now you can see why the preponderance of Sri Lanka's present-day biota has its roots in Southeast Asia and tropical Africa. But if the ancestors of our present-day fauna and flora had their roots in Asia and Africa, how did they get over here? There are many ways in which propagules such as seeds can disperse overseas. Overseas meaning, for example, from India to Sri Lanka across the Palk Strait. They can be carried by the wind, they can be carried by birds or bats, or even on the sea, on rafts of vegetation, for example. Some animals too can benefit from such routes, as the rich biodiversity of oceanic island groups such as Hawaii and the Galapagos attest. These are separated from mainland continental regions by hundreds or thousands of kilometers of Pacific Ocean. But for the most part, plants and animals disperse the hard way, on land. Now, if you think about it, freshwater organisms are especially interesting when it comes to biogeographic studies. They must have not only land connections, but also rivers and streams through which to get from one place to another. Because of this, Hiranya and I chose to focus our attention on freshwater fishes. This was handy because we like fish anyway, at least in my case, not to eat but to study. As it happens, I'm a vegetarian. Now remember that in order to get to Sri Lanka in the first place, fishes originating in Asia and Africa had to enter India from the north and then swim across all the river basins of India, all the way to the south. That isn't easy because most of the rivers in peninsular India flow east-west. Then, having got to southern India, they had to get across to Sri Lanka through the Palk Isthmus. Remember, because they were freshwater fishes, they couldn't swim across the sea. So whenever the Palk Isthmus was above sea level, it was possible for these fish to swim over, so long as rivers and waterways existed on the isthmus. So let's have a look at those molecular clocks we talked about a minute ago and see what they say. This is the molecular phylogenetic tree, the family tree as it were, of the gouramis and their relatives. It was generated by Dr. Lucas Ruber at the Natural History Museum in Bern. These are pure freshwater fishes, and you can see that they all derive from a common ancestor which lived in the Eocene around 50 million years ago. From there, two branches or clades diversified. One of these contains African species, which you can see at the bottom, and the other contains Asian species. So let's have a look at the three genera in the group that occur on Sri Lanka: Pseudostronymous, Malpolutta, and Belontia. I suspect nature enthusiasts amongst you will be familiar with all three of these. Now, this phylogenetic tree shows up some really interesting things. First off, you can see that Pseudostronymous and Malpolutta are each other's closest relatives. But taken together, their closest relatives are in the genus Macropodus. But you don't find Macropodus in Sri Lanka. You don't find it even in India or in Bangladesh or Burma or Thailand. It's found in East and Southeast Asia. How's that for a cool disjunction? And you can see from the time scale shown on the x-axis here, the Sri Lankan lineage and the Asian lineage diverged at around 28 million years ago. That's an important date, so bear it in mind. Now let's have a look at Belontia. There are only two species of Belontia. One is endemic to Sri Lanka, and the other is found in the peninsula of Malaysia, in southern Malaysia, and on Sumatra. And what do you know? The two species of Belontia, too, diverged 28 million years ago. So we have no choice but to infer from these distributions that ancestral Pseudostronymous, Malpolutta, and Belontia must have inhabited India at some point in their past. After all, they are pure freshwater fishes, and they can't survive more than a few minutes in seawater. So they can have reached Sri Lanka only through India. So what made them disappear from India, Myanmar, Bangladesh and Thailand? Here again, the only culprit we can think of is climate. We know that the climate of the Indian peninsula became very dry and strongly seasonal sometime after 6 million years ago, like Sri Lanka's dry zone is even today. But the wet zone seems to have been a perhumid refuge for pretty much the whole of the past 30 million years or more, though it too shrank to a dangerously small size during some of those aridification events. So now you begin to see why these ancient lineages such as Belontia became extinct on India but persisted in Sri Lanka's wet zone. It wasn't the amount of absolute precipitation that made this possible. It was the absence of a long dry season, a perhumid climate. If these fishes entered Sri Lanka around 28 million years ago, the Palk Isthmus obviously would have had to be above sea level at the time. In fact, this might have been the first occasion on which it was emergent, or around that time, since Asia and India made contact around 55 million years ago. We know that sea level went down by about 250 meters at around that time. So that's another piece of evidence that adds some credence to our model. And given that Sri Lanka was slap bang in the middle of the intertropical convergence zone at the time, a rainforest corridor could well have existed between Sri Lanka and India then. In fact, such a corridor has to have existed if wet zone species were, or the ancestors were to have dispersed to Sri Lanka. And the Palk Isthmus was the only corridor through which plants and animals could enter Sri Lanka. Now have a look at the sea level graph one more time to remind yourself that the isthmus was above sea level for most of the past 5 million years. That's a very long time. The red line here shows the present sea level, and you can see that we were connected to India multiple times over the past 5 million years. So you might expect most South Indian freshwater fishes to have crossed the isthmus into Sri Lanka over those 5 million years. But they didn't. In the case of freshwater fish alone, 14 whole families that are present in South India failed to make it to Sri Lanka. And that was over a period of millions of years. And it wasn't just fish that had problems. Take, for example, the Sri Lanka jungle fowl and the toque macaque. Both these are common even in the arid region around Mannar at the Sri Lankan end of the Palk Isthmus. But strangely, they remain endemic to Sri Lanka and seem to have been isolated here, unable to cross the isthmus. On the Indian side, the great Indian bustard had a range that extended right down to the southeastern plains of Tamil Nadu. But it was unable to cross the Palk Isthmus into Sri Lanka. Now remember that this is a bird that's especially adapted to life in an arid landscape, like the most arid parts of Sri Lanka. Why then couldn't it cross the Palk Isthmus? And then there's the spotted owlet. You find it over much of Asia and right down into the southernmost tip of India, but it never seems to have crossed into Sri Lanka. But I need to point out that some animals may have entered Sri Lanka but not found ecological niches here that suited them. It seems that the bayback shrike might be such a species. It's able to fly across the Palk Isthmus, and we know that even today the occasional vagrant occurs in Sri Lanka, but it never became resident here. So it turns out that although the Palk Isthmus was well above sea level for most of the 5 million years and more than 100 kilometers wide, it served not so much as a highway for biodiversity but as a roadblock. Very few animals successfully crossed it during the whole of that time. And that's millions of years. Once again, we think that the most likely reason for this was that it was simply too arid. This hypothesis is supported by a lot of data, but it remains to be properly tested. And it can be tested by drilling down and extracting cores which will show what plants grew on the Palk Isthmus at various times in the past. Take, for example, the dragon lizards of the genus Sitana. These ground-dwelling lizards are associated with extremely dry and open habitats. In India, Sitana ponticeriana occurs in the arid, dry region around Rameshwaram. And on the Sri Lankan side, a very close, in fact, almost genetically identical species occurs around Mannar. Their common ancestor clearly crossed the Palk Isthmus. But on the Indian side, there is also a second species, Sitana visiri. It too is associated with very arid habitats, but it seems never to have made the crossing into Sri Lanka. Perhaps few species illustrate the aridity of the Palk Isthmus better than the tarantula Poecilotheria hanumavilas sumica. I love saying that name. Arachnologists discovered this spider in India only about 15 years ago, and it turns out to have a very narrow range, just the immediate vicinity of the Rameshwaram area in Tamil Nadu, on the Indian side of the former Palk Isthmus. Now, if our hypothesis is correct, its association with xeric, that is to say, super-arid habitats, means that it should have occurred on the isthmus itself, so we should have found Poecilotheria there. But of course, the isthmus is now underwater. But then, the species should occur also in the most arid parts on the Sri Lankan side of the isthmus, around Mannar. And that's exactly what turned out to be the case. In 2015, Ranil Nanayakara and his colleagues discovered Poecilotheria hanumavilas sumica. Yes. I challenge you to say that after a couple of beers, in Talemana Island. And the fact that it hasn't been recorded from anywhere else in Sri Lanka up to now suggests that it might be specialized to that very arid climate. But as convenient as such examples are, they don't provide us with a detailed account of the conditions on the isthmus itself. So let's look a little more closely at its geography. On the Sri Lankan side, the two main rivers that flow towards the isthmus are the Kala Oya and the Malbata Oya. Remember that what we have outlined here are the basin boundaries, not the tracks of the rivers themselves. Now, P.E.P. Dharanegala showed almost 70 years ago that the Kala and Malbata were once confluent and made up a single river basin. And the northern Knuckles Hills, which now drain into the Mahaveli Basin, at that time drained into the Kala-Malbata system. Now on the Indian side, the main rivers that flow towards the isthmus are the Vaigai, the Vaipar and the Tamiraparani. In the course of the last few years, Indian hydrogeologists have shown that these rivers were once confluent with Sri Lanka's Malbata and Kala rivers on the Palk Isthmus. In other words, there was a freshwater connection between India and Sri Lanka. If this were in fact the case, you might think we might expect to see some similarity between the freshwater fishes in the Indian and Sri Lankan rivers. Well, this is where the value of Hiranya's work on freshwater fishes really shows itself. He's studied a lot of different groups of fishes, but I'll focus on just one genus, Dawkinsia. There's an endemic species of Dawkinsia in Sri Lanka, a beautiful little fish called Dawkinsia srilankensis. We find it in streams draining the northern hills of the Knuckles. Now you'll remember from a moment ago that these hills used to be drained by the Malbata-Kala river system. And what do you know? The species that is most closely related to Dawkinsia srilankensis in the molecular phylogenetic tree that came out of Hiranya's data is Dawkinsia thamrapanii. The molecular clock shows that the two species diverged around 3.7 million years ago in the Pliocene. And where does Dawkinsia thamrapanii live? It is endemic to the upper regions of the Tamiraparani River in India. It's clear from this that a hydrological connection previously existed between the Tamiraparani and the Kala-Malbata system across the Palk Isthmus. And the molecular clock has helped us estimate when that connection ended, around 3.5 million years ago in the Pliocene. Thing is, despite this hydrological connectivity, dispersal across the Palk Isthmus seems to have been very difficult indeed. For example, those 14 families of South Indian freshwater fishes I mentioned couldn't make it across to Sri Lanka. Take the example of the freshwater crabs. Sri Lanka has a diversification of well over 50 species of freshwater crabs, almost all of them endemic to the island. These are in 7 genera, 5 of which are endemic to Sri Lanka. A group of us led by Dr. Natalie Bainertz and Mohammed Bahir showed that they all evolved from a common ancestor that dispersed into Sri Lanka around 7.5 million years ago. No other freshwater crab ever made that crossing from India to Sri Lanka again for the past 7.5 million years. Isn't that amazing, seeing as these crabs commonly occur also in the dry zone? Well, amongst those dry zone crabs are several species of Osiotelphusa. One of their ancestors migrated back to India across the Palk Isthmus about 5 million years ago. But that was the last time. No freshwater crabs ever crossed the isthmus again, even though it was above sea level for much of the past 5 million years. Hiranya's work too supported the idea that the region of the Palk Isthmus that at some point in the past, or perhaps more accurately some points in the past, suffered catastrophic aridification. I'll take just one example, the stonesucker Garra silonensis. This is an endemic species that occurs in flowing waters throughout the country, in both the dry zone and the wet zone. This makes it an especially useful model for biogeographic analysis and also for phylogeographic analysis. Phylogeographic studies investigate the genetic mutations that occur within the various populations of a species, which helps us understand how these populations evolved and are related to each other. If you look at the phylogenetic tree of Indian and Sri Lankan Garra, you see straight away that Garra silonensis, which this green box indicates, diverged from its sister group, the Indian species Garra mulia, around 3.7 million years ago. Now, you might remember that was about the time that Dawkinsia srilankensis diverged from Dawkinsia thamropanii, before the great Pleistocene aridification of the Palk Isthmus that we infer from other studies as well. What's more, Garra silonensis occurs as 8 distinct genetically characteristic clusters or clades. As it happens, the geographic distribution of these clades is quite informative. The various clusters are distinguished by characteristic haplotypes. Hiranya's depicted the distribution of these haplotypes in this diagram here. For our purposes today, we can consider these to show the distribution of shared genetic mutations across the populations of Garra. From this and from the phylogenetic tree, he made some really interesting discoveries. Let's have a look at a few of these. Now we know that Garra must have entered Sri Lanka via the Malvatukala river system. So you'd expect the basalmost population, that is to say the population closest to the root of the phylogenetic tree of Sri Lankan Garra, to be resident in those rivers, in the Malvatu and Kala. But no, it's exactly the opposite. The basalmost population in Sri Lanka is the one in the far south of the island. Now you can see that that's a completely unexpected result. So how do we explain it? The only explanation seems to be that the Malvatukala river system at some point dried up and the Garra in it were extirpated. And then those rivers were recolonized by populations of Garra that had survived in humid refuges in the wet zone. And that's exactly what the haplotype analysis shows. The populations of Garra that now inhabit the Malvatu and Kala rivers originated in the middle region of the Maha Valley. Now, isn't that cool? We describe several other studies that support these conclusions in our book, in several other genera of fishes as well. There is a growing body of data that shows that Sri Lanka, and especially the Central Mountains, suffered at least one, and very likely several, catastrophic extinction events in the past 3 million years or so. And aridification is most probably why highland streams above 1600 meters contain no native freshwater fishes even today. This is also probably why Sri Lanka has no fish lineages with so-called rheophilic specializations, that is to say, specialized for life in fast-flowing waters, apart from Garra, that is. There are many such families in South India. By now you might be wondering when exactly Sri Lanka's familiar large mammals got here. The elephant, the leopard, the bear, the spotted deer, the sambar, and so on. Well, we don't know for sure, but my guess would be that they're all quite recent immigrants in the last few tens of thousands of years. All our large mammals are adapted to life in highly seasonal environments. There isn't a single species that's confined to the wet zone. By contrast, South India has several wet-adapted large mammals, the gaur, the lion-tailed macaque, the Nilgiri tahr, and so on. So let's sum up what these studies show. First and most important is the fact that Sri Lanka's fauna and flora is special mainly because of the per-humid climate of the southwestern wet zone. And second, aridification caused major extinctions on this island in the recent past, meaning the last few tens of thousands or few millions of years. And finally, there is the discovery that the Palk Isthmus, rather than serving as a biodiversity corridor between India and Sri Lanka, acted as a barrier or a filter for much of the time. If not for its aridity over the past few million years, Sri Lanka's biodiversity would have been much richer than it is even now. In other words, for better and for worse, our biodiversity has been shaped by climate. And that's another reason why conservation management based on sound science, including climate science, is so crucial. And this matters not just to wildlife, but also to agriculture, which is something we should bear in mind going forward. Thank you very much for your attention.